So today we're going to be looking at 2022 higher level paper 1, question 6 for maths. Differentiate f of x, which is equal to 2x squared plus 4x with respect to x from first principles. Easiest way I find, and it's the way I always do it, I'm just going to regularly differentiate this just to figure out what the answer is going to be. So it's minus 1 from the power multiplied by the whole power. So we're going to end up with 4x plus 4. So at the very end, what I'm going to be able to do is just look straight back up here, and this is going to be my answer. Once you do a few first principle questions, the process should kind of get burned into your memory. So it's a 5-step process. The first part is just going to be f of x. Second step, we have f of x plus h. Third step, we have f of x plus h minus f of x. Fourth, f of x plus h minus f of x all divided by h. And the final step, we have f of x plus h. We have the limit, as h goes to 0 of f of x plus h minus f of x all over h. If a question like this comes up in the Leaving Cert, it should be gimme marks. Like, it should be something that you don't even have to think twice about. It's just the same process that you follow time and time again. So that's the steps we're going to follow. So if we do it over here, we're just going to be using the 2x squared plus 4x. So f of x, well, that's just 2x squared plus 4x. Step 2, wherever I see an x, I just substitute in x plus h. So I get 2 times x plus h squared plus 4 times x plus h. And if I simplify that, that's the same thing as 2 times x squared plus 2xh plus h squared plus 4 times x plus h. Again, simplify this, we're going to have 2x squared plus 4xh plus 2h squared plus 4x plus 4h. Step 3, we're going to take away f of x from what we just figured out. So if I take everything that we just figured out there, and I subtract 2x squared plus 4x, what you're going to see is that we're going to get some cancelling going on. So there's a 2x squared on the left and the right, one subtracts the other, these cancel. And again, there's a 4x on either side, both positive. We subtract one from the other, 4x, they disappear. So the end, what we're left with is just 2h squared plus 4xh plus 4h. Step 4, we're going to divide by h. So we have 2h squared plus 4xh plus 4h. Divide this by h. Well, h goes into h squared h times, so this is going to be equal to 2h. H goes into 4xh, well, the h is just cancelled out, so we get 4x. And h goes into 4h once, so we just get 4. Now the final step, we take the limit as h goes to 0. So in this step, wherever we see a h in the final step, we can just sub in 0, and that gives your answer. So if we sub 0 into that, we're going to have 2 times 0, which is 0. We can't sub it into anything else, so then we just get it equal to 4x plus 4. And if we take what we just figured out there and look right back up at the very top, we know we've done it correct. There's another video on this channel explaining why we use first principles, why it works. It explains it using the slope formula for slope that you would have learned during coordinate geometry. It's an extension of that into calculus. And if you're really struggling, you don't understand why these steps actually produce the derivative, go take a look at that. Highly recommend it. So, part B. A rectangle is expanding in area. Its width is x centimeters, where x is a real number and x is strictly greater than 0. Its length is always 4 times its width. So that's the first thing we should take note of. Find the rate of change of the area of the rectangle with respect to its width, x, when the area of the rectangle is 225 centimeters squared. So, when in doubt and you're given a question like this, it might make more sense just to draw a little picture, just so it might make more sense in your head. So we have a rectangle where its length is always 4 times its width. So if we have to represent it in terms of x, its width we can write as just regular x, where its length we can write it as 4x. We also know that the area is equal to length by width. So in this case, we have the area is equal to the length, which is 4x, multiplied by its width, x. So that's going to be 4x squared. In other words, whatever we plug in for x, because it's going to be the same value, it's going to produce the area. So if it makes sense, we can just write it there as well. Now, find the rate of change of the area of the rectangle with respect to its width x. So up here, we've basically created a formula for its area. So if we want to find the change of the area with respect to x, what we have is dA, small change in the area, in response to a small change in the x value. Well, dA dx is just going to be the derivative of 4x squared. So if we were to find a prime, we'd have 8x. So this thing is going to equal to 8x. And that's something we're going to use later on. Now, find the rate of change of the area of the rectangle with respect to its width x when the area of the rectangle is 225 centimeters squared. So we can use this because we have a formula already created for the area. So we now know the 4x squared is equal to 225. So if we solve this, we have x squared is equal to 225 over 4. So x is going to be equal to the square root of 225 over 4. Now, all we're going to be doing, we have its area in terms of x. How do we know how much to change it by? Well, we're going to substitute x into dA dx. So we're going to be putting this value here into this x here. Because dA dx, well, that tells us how much the area is changing when we change the value of x. So in the end, what we're going to have is 8 multiplied by the square root of 225 over 4. And when we calculate that, what we're going to have is 8 multiplied by 15 over 2. And that's just the same thing as 60 centimeters. So in the end, what we have is a change of 60 centimeters squared, because we're dealing with area, per centimeter. And this right here is going to be how much it's changing when we change the value of x. Part C. The graph of the cubic function px is shown in the first diagram below for some value of x between 0 and 4. X is a real number. The maximum value of p prime of x in this domain is 1, and p prime of 0 is equal to negative 3, where p prime of x is the derivative of px. Use the information to draw the graph of p prime of x on the second set of axes below for some value of x between 0 and 4. So, there's a few things we can take from this. First of all, looking at this top graph here, we can see that it's a cubic and it's a negative cubic. So that's one thing we should take down first of all, so it's negative. What happens when we differentiate a negative cubic? Because this is equal to p, if we find p prime, well, we're going to be given a quadratic. And more importantly, we're going to be given a negative quadratic function. So first of all, if we're drawing p prime on the bottom graph, we know that it has to take this form. Well, what else do we know? It says that p prime of 0 is equal to 3. So whatever I found the derivative of p and I plugged in 0, it gave me negative 3. So at the bottom, if we plug in 0, if we were to go to 0 on the x-axis, when we plug that in, it gave us this value of negative 3. So that's the first thing we can take note. It also says that the highest value in this is going to be 1. Which we have just here. So I know I can't go above 1 right here. So, some other facts we know. The turning points of any cubic equation is going to be the exact same as the roots of the associated derivative or the associated quadratic. In other words, if we have p here, p prime is going to be this full function down below. So if I were to take my roots, which is here, and drop them straight down, that's going to give me my two roots here. In other words, my roots of this quadratic are going to be at the point 1 and 3. So I'm going to get rid of those for the time being. So I know that my roots are going to be here and here. I also know that the highest point is going to be 1. So in between 1 and 3 on the x-axis, I can only go as high as 1. So 2 is going to be 1. Another way we can figure this out is when we have p of x, which is the top function here. If we find p prime of x, it's going to tell us the rate of change of p of x. And more importantly, if we find p double prime of x, it's going to be equal to the point of inflection. For a cubic, when we double differentiate it and find p double prime of x, it gives us the point of inflection, which looking at this graph is going to be right here. It's the midpoint between the two turning points, and it's also where it goes from concave up to concave down. In other words, if we were to divide this in half, we have sort of a U-shaped graph on the left and we have an N-shaped graph on the right. The left one, so this one right here, that's going to be concave up because the two arms are pointing up. And here we have concave down where it's pointing down. The point of inflection is going to have the greatest value or the maximum value of p prime of x. So the point of inflection, if we go back up here, it's the max it can get to. It could be the minimum as well if it was negative, or if it was positive, sorry, but it's going to give us the maximum value in this case. Finally, because this goes through the point -3, 1, and then 2, 1, and then 3, it also goes through the point -3, 4. So given that this is going to be the maximum value, we now know that 1 has to, as it says in the question, is the greatest value, and it's also going to occur at the point of inflection. Again, if we drop the point of inflection down to this graph, we get it right here. So it happens at the point 2. And if we go ahead and just connect all the dots, then what we have is a negative quadratic equation that's going to look something like this, where it passes through the points 0, -3, 1, 0, 2, 1, 3, 0, and -3, 4. Sorry, 4, -3. And there we have it. It's a unique question. I haven't seen something like that in a while. That's a good question. It tests how well you know what actually happens in calculus when you differentiate certain functions. Any questions, just let me know and I'll get back to you in the comment section, or by all means I'll post another video just explaining what happens when we differentiate.